All right, this is video 21 for the Baby Rule Analysis series, and in this video we'll talk about some of the concepts of continuity of functions. And so there's a good bit of terminology that we're going to discuss in this video, and then in the following videos we'll go into more examples. But for continuity, the last couple of videos dealt with limits of functions in the real number line. So for continuity of functions, there's a certain relation with limits of functions. So recall for a limit of a function, I wrote down the definition that if you have a function from set A to the real number line, you let C be a cluster point of A, then the limit of f of x as x approaches C equals L if and only if for all epsilon bigger than 0, there exists a delta greater than 0, so that for all x and a, if 0 is less than the absolute value of x minus c, which is less than delta, then the absolute value of f of x minus L is less than epsilon. And this thing that we had as the 0 less than the absolute value of x minus c less than delta, I like to call that a punctured neighborhood around C. So it's like a delta neighborhood around C, but with C taken out. So for all x, and it's in the delta neighborhood around C, but subtract out C. In other words, it's all x where x is distinct from C in the delta neighborhood. Then we have that for this part, the absolute value of f of x minus L less than epsilon corresponds to any f of x that's in the epsilon neighborhood around L. So in terms of neighborhoods, we would say limit of f of x as x approaches C equals L if and only if for all epsilon there exists a delta, so that for all x in the punctured delta neighborhood around C, then f of x is in the epsilon neighborhood around L. And then we had the sequential criterion for the limit, which basically says if you have for all sequences xn part of A subtract out C, if xn converges to C, then f of xn converges to, that's incorrect, L. Okay, that was the sequential criterion. And graphically, this is what we were looking at in terms of limits. And notice on the x-axis, I have the open interval in green, and then in the center is C, and the center is an open dot. All right, that's the punctured neighborhood, and it's a delta neighborhood, so the radius of this punctured neighborhood around C is delta. And so we're C plus delta, and then C minus delta. All right, and we are focusing on the x's in this puncture neighborhood, and we are only caring about the x's around C, not C itself. So for the x's that are around C, we want it to be so that the corresponding, so f of x value is within epsilon of L. So we have some arbitrary x where it's f of x is in the epsilon neighborhood around L. So that's graphically what we're looking at here. And the main thing is that we're only caring about the x's around C in this punctured neighborhood, not C itself. So for continuity, we do care about C, and that's whether it's a cluster point of A or not a cluster point of A. In the case that C is a cluster point, so for continuity, if C is a cluster point of A, we basically need the function evaluated at c, f of c, to equal the limit as x approaches c of f of x to be continuous at c. That is, we need these three conditions. F needs to be defined at c so that f of c makes sense. The limit of f at c must exist so that limit of x approaches c of f of x makes sense. And then these two values must equal. So limit x approaches c of f of x equals f of c. All right, and that is when we're dealing with the cluster point c. Now recall that if you have a cluster point, what that means is if you have any punctured delta neighborhood and you intersect it with the set A, then that intersection is non-empty. So graphically, I drew an open interval A, where capital A is endpoints are A and B, open interval. And then I focused on just the endpoint A, and the endpoint A in this case is a cluster point of A, because if I draw any delta neighborhood around A, where you don't include A, so it's the punctured delta neighborhood. So this is punctured. So that's why there's an open dot around A. Then there's going to be members of A in that punctured neighborhood, of capital A in that punctured neighborhood. So namely these guys right here are members in set A. So that's for an arbitrary delta punctured neighborhood around that particular endpoint A, little a, and that means little a in this case is a cluster point. But yet little a was not actually a part of the set A itself. All right, so the cluster point could be in A or not in A. Now, we didn't talk about what is, if this value C is not a cluster point. And if it's not a cluster point, it's called an isolated point. And what it means to be not a cluster point, we just take the negation. So taking the negation of for all delta greater than 0, the intersection of the punctured delta neighborhood around C intersecting A is non-empty. The negation of that is there exists a delta where the punctured delta neighborhood intersecting A is empty. And that's true if the delta neighborhood itself around C intersecting A is the value C itself. So this one is just a regular delta neighborhood around C. All right, so the regular delta neighborhood around C intersecting A is only the value C. All right, that's what it means for it to be an isolated point. And just as a picture, let's say that's my real number line. And we'll say this is A. And I'll give this A and B. And then let's say you have some point out here, and I'll call that point C. So then A is the union of this open interval AB and the singleton Z. Now, this value Z, this is going to be our isolated point. And Z is a member of A. So if we draw a delta neighborhood around Z, So I'll use that. Let's say this is and I'll use delta. Actually, it doesn't necessarily matter. So let's draw a delta neighborhood around C. Let's say this is my delta neighborhood around C. So this is Z plus delta, and then this other is Z minus delta. Now the intersection of the delta neighborhood around Z with A is the center point Z itself. So it's only the value Z. All right, and if I use it in terms of punctured neighborhoods, because that's what we're dealing with, a cluster point, so for it to be a cluster point and for it to not be a cluster point, that means there exists a delta neighborhood, so that the punctured neighborhood around whatever our value C is, and we intersect that with A, and it's the empty set. So if we draw a delta neighborhood around Z, but in this case, it's going to be a punctured delta neighborhood. So let's say this is our delta neighborhood. This time it's going to be punctured, so we exclude our center value C. All right, so since we exclude that, then there are no members of A. So there are no members of A. Because we're excluding, there's an open dot at C, so excluding C. So that means it's an empty intersection with the set A in this delta neighborhood. In other words, the delta neighborhood, if it's just a regular delta neighborhood around Z intersecting A, is the empty set, or is the set Z. Whereas if we had the punctured delta neighborhood, meaning we have the delta neighborhood around Z, but subtract out Z, and then we intersect that with A, since it's punctured, we exclude Z. So since we're excluding Z, Z is an element of A, and everything else is in this delta neighborhood is not an element of A, then this is an empty set. All right, so that case is that's an isolated point. Okay, so for isolated points, F is going to be automatically continuous at C, and these points, though, are of little practical interest to us since they have no relation to a limiting process. So to summarize, for continuity, we're going to include C in our discussion. So what it means to be continuous, you have a set A, where the function f goes from A to the reals, and you have any value C in A. F is continuous at this value C, means that for all epsilon, there exists a delta, so that for all x in A, the absolute value of x minus C less than delta implies that the absolute value of x minus f of C is less than epsilon. So some key differences between this and the limit definition. This one strikes out. So that's has x minus C less than delta, whereas the limit definition had 0 less than absolute value of x minus C less than delta. In other words, C is allowed to be x itself. So for the limit definition, x was distinct from c, and for the continuous definition, it's possible that x can be c. So that means we're dealing with just a regular delta neighborhood. And then another key difference was that for the limit definition, we had the absolute value of f of x minus L to be less than epsilon. Whereas in the continuity definition, we have it so it's absolute value of f of x minus f of c is less than epsilon. And c is any value c in the set A. All right, so those are some key differences in the definitions. So it's very similar to the limit definition. It's just now we do include our value c into consideration for continuity. And our L in this case, and the capital L is going to be f of c. Note that for isolated points, since there exists a delta greater than 0, where the intersection of the delta neighborhood around C and intersecting A is the singleton set C, then it's trivially true that f is continuous at an isolated point C, since the difference of x minus c is really just c minus c, which is 0, and that's definitely less than a delta greater than 0. And so, which would also imply that if we had f of x minus f of c, since we're just only the singleton set, then it's just f of c minus f of c. And that's 0, which is less than epsilon. So isolated points is trivially true. And so we're going to focus our attention on testing continuity at just cluster points. So graphically, this is the picture representation for continuity of a function. And notice it looks very similar to the one that we had for limit. Now here we have, we're including C in our delta neighborhood. And so f is continuous at C if and only if given any epsilon neighborhood of f of c. In this case, where instead of for the limit we had L, in this case it's going to be f of c in place of L. So we have an epsilon neighborhood around f of c. So given any epsilon neighborhood, there exists a delta neighborhood around c, so that if you intersect, so that if x is an element of the intersection of A intersecting the delta neighborhood around C, then we have that f of x is an element of the epsilon neighborhood around f of c. All right, that's equivalent to our definition of continuity right here, just written in terms of neighborhoods. And so here it is, written more explicitly. So we have a function f from a to the reals is continuous at c, which is c is an element of A, if and only if given any epsilon neighborhood, which we do v and then subscript epsilon, and then f of c in parentheses. So given any epsilon neighborhood of f of c, there exists a delta neighborhood, and this is not a punctured delta neighborhood now. We're just considering just a regular delta neighborhood. So delta neighborhood around c, such that if x is any point that belongs to the intersection of A and the delta neighborhood around C, then f of x belongs to the epsilon neighborhood of f of c. So that is if you have the function of the set of the intersection of A intersecting the delta neighborhood around C, that set itself is entirely contained in the epsilon neighborhood around f of C. All right, so that's the neighborhood definition for continuity. Now the sequential criterion for continuity is that if you have a function f from A to the reals, it's continuous at some number C in A, if and only if, for every sequence xn of A, if xn converges to C, then f of xn converges to f of C. All right, so now our sequence xn is a set in A, and it's for the limit definition for sequential criterion, it was a set of A subtract out C, so we're including A. Now, if C is an isolated point of A, then the only sequence where xn converges to C is the constant sequence. So it's only true if we have just a sequence of only C's. So this is what it means for the function to be continuous at a point C. Now, for a function to be continuous over a set B, it needs to be continuous for every element C in that set B. Makes sense? So continuous at every single number C and B, then it's continuous over that subset B. All right, so some examples. And the first example, if we have the function g of x equal to x, it's continuous on the entire real number line. So we've shown before that for limits, if we had the limit as x approaches c of x, that's equal to c. So since we've already shown that, and since it's true that if you evaluate c in the function g, you get c. So since that's true for all c, then g of x is continuous at every point c in the real numbers. All right, and that's it. We just needed that the limit exists. G of c is defined, and that the limit as x approaches c is equal to the g of c, which it is because g of c is equal to c. Now, if I try to use the definition, the delta epsilon definition for continuity, this is how you would do it. So for proof 2, you just let C be any fixed real number given epsilon. If we pick delta to be equal to epsilon, then we have for any x in the reals, the absolute value of x minus c less than delta implies that we have the absolute value of g of x minus g of c, which evaluated for each of those is x minus c. And x minus c we know is less than delta, and since delta is equal to epsilon, then this g of x minus g of c absolute value difference is going to be less than delta equals epsilon. All right, so this is just using the definition. And our first proof was using examples of limits that we've already proved. All right, so for the next example, if you had the square function, f of x equals x squared, it's continuous on the reals. And so I'm only going to do it since we've already proved that for limits that if you have x approaches c, x squared is equal to c squared. All right, so we've proved that. But since f of c equals c squared for any c in the reals, that means f of x is continuous. All right, so we've already proved this. And since f of c is c squared, then f of x is continuous. And the delta epsilon proof for this would be like the delta epsilon proof that we did for the limit version of x squared equaling c squared. So I'm going to spare us the details for that. Now consider this example. If we had f of x equal to x squared plus x minus 6 divided by x minus 2. Now this is an example of a function that's not continuous for the entire real number line. So why is that? It fails to meet the requirement that f of c is defined for every c. So again, we have three requirements. We need f of c to be defined. We need the limit of f of x as x approaches c to exist. And we basically need these two values to equal each other, that the limit of f of x as x approaches c equals f of c. That's the requirements. So in this example, f of c is not defined for every c. For instance, f of 2, if you plug 2 in, it's not defined. And graphically, this is what it looks like. So you have a hole in the graph at the point 2 comma 5. All right, so there's that hole, so it's not defined at f of 2. But we know the limit does exist as x approaches 2. All right, so from looking at it, we could say that the limit x approaches 2 of f of x equals 5. So that's what I claim just by looking at the graph. Now I'll prove that claim. So the question is, we have this function. It's not continuous at every number because it's not continuous at the value 2. And that's because f of 2 is not defined because there's a hole in the graph at x is 2. But yet we do have the limit of f of x as x approaches 2, that limit exists. And looking at it, we could say the limit actually is 5. Now, is there a way that we can make this function continuous? And you can make this function continuous just by closing the dot, so that where the open dot is, just enclose it, and that'll make the entire function continuous. This is called a removable discontinuity. So I'm going to first prove that the limit as x approaches 2 of f of x is 5. So that's what we need. And then I need to extend this function so that we have it to be 2 of 5 existing as a point. All right, so first prove the limit part. All right, so the claim is that for the function f of x equals x squared plus x minus 6 divided by x minus 2, we claim that the limit as x approaches 2 is 5. And the proof is in green. So given epsilon, you just pick delta to equal epsilon. Then for all numbers x in the reals, and again, this is the limit proof. That's why I have that the 0 is less than the absolute value of x minus 2 less than delta. All right, so again, this is for the limit definition. So if we have that, then we have that the absolute value of x squared plus x minus 6 over x minus 2 minus 5, which is equal to, and we can factor the numerator to get x plus 3 times x minus 2. And then the x minus 2's divide out. And we can divide these out, so we don't have to worry about dividing by 0. Dividing by 0 here because we're only considering x where 0 is less than the absolute value of x minus 2 less than delta. Okay, so since we are not dividing by 0, then we can cancel out the x minus 2's. That gives us x plus 3. So then we have the absolute value of x plus 3 minus 5. Well, that actually equals x minus 2. And since we already said we have x minus 2 being less than delta, so then this is less than delta, which is equal to epsilon. All right, so that proves that the limit as x approaches 2 of f of x is 5. All right, so that's that requirement. So the limit exists in the real numbers, the limit is 5. Now to make the function continuous, we need f of 2 to be defined. So we can extend this function f of x to be capital F of x, where at capital F of x, if I define it to be little f of x, where x is not 2, but capital F of x equals 5 for x is 2, then this will make the function capital F of x to be continuous, because we can have capital F of 2 is defined, it's equal to 5, and then the limit as x approaches 2 of capital F of 2, that's going to be equal to 5, since that's also equaling the same as limit x approaches 2 of little f of x. Okay, so this should have been x. All right, so then now that we have that, then we can say we have a continuous function. Capital F of x is our continuous function. And note that this example had a removable discontinuity. So in other words, we basically looked at this graph of this function. It had a hole at the point 2, 5. It wasn't continuous there because there's a hole, and meaning that f of 2 is not defined. But the limit did exist. The limit was 5. I proved that the limit was 5, this in green. And then we changed it to where we enclosed this hole by creating a new function called capital F of x. All right, so here's another example, and this case is a removable discontinuity. Now this next example, let's say we had the f of x equal to the absolute value of x divided by x, for x is not 0. Now this is not continuous. Now I wrote down, this is the definition of absolute value first. All right, so absolute value of x is x if x is greater than or equal to 0, or is negative x if x is less than 0. Note that for our function f of x, if x is bigger than 0, then we get 1 for f of x. If x is less than 0, then we get negative 1 for f of x. And graphically, this is what it looks like. So we definitely have these holes at 0, and there's no way to patch this up and to extend this to a continuous function because there's this gap that I sort of drew in orange. So there's this gap that we can't account for to make this and extend this into a continuous function. And that's because of the limit as x approaches 0 of f of x doesn't exist, because the left side limit of 0 is negative 1. The right side limit of 0 is 1. So the limit as x approaches 0 doesn't exist. Now this is a case where we can't extend this to a continuous function. And this is a non-removable discontinuity. At 0. So from these two examples I just went over, there's two remarks. The first remark is that if you have a function from a to the reals, and it's not continuous at c because of the fact that f of c is not defined, but f of f does have a limit. That's in the reals at C. Then we can extend this to a function called capital F, where we take the union of the domain of A with the singleton set C to the reals, and we define it by letting capital F of X equaling this value L for X equals C, and then equals little f of X for X in the set A. And then our capital F will be continuous at C. So we can make this a continuous function, and this involved a removable discontinuity. And that was like this example where we had the x squared plus x minus 6 over x minus 2. We changed it to this capital F of X. And this would be like our L for X equals C. And this would be like our F of X for X in our set A. Okay, so that's the first remark. And so we can make it a continuous function. We can extend it to a continuous function if we have the limit existing, even though f of c is not defined. Now the second remark is that if we had the function where g doesn't have a limit at c, then there's no way to obtain a function that's in a continuous function, capital G, in the same fashion that we're doing for this capital F. So there's no way to obtain a continuous function by using the same thought processes for Mark 1. And that was like where we had this one, where we had a limit not existing at 0. So if the limit doesn't exist at that particular value, C, then we can't define it in such a way to make it continuous. Because to observe, if limit as x approaches C, if capital G of X exists and it equals capital C, then that would mean that the limit of little g of X as x approaches C must also exist and equal C. So, but we can't have that because we're saying that the limit as x approaches C if little g of X doesn't exist. All right, so those are the two remarks for two different discontinuities, but yet one of them we were able to extend the function to a continuous function, and the other one we cannot extend the function to a continuous function if we use the same thought process. And then we talked about continuity as far as what it means, and we have the 3 requirements. And C, we are interested in cluster points of A, not isolated points, because at isolated points it's trivially continuous since we have the absolute value of the difference of x minus c to be 0. All right, so for cluster points, we need it to be f's defined at C. The limit of f at C exists, and these two values limit x, as x approaches C of f of x equals f of C. All right, so that's the requirements, and then we talked about this delta epsilon definition, which to this stage, since we've already dealt with limits, we've already proved these type of things with limits, then the proof regarding continuity, I try to avoid having to use the delta epsilon definition over and over for continuity if I don't have to. Okay, so that's it for this video. Next video, I'll go into some examples and then talk about combinations of continuous functions.